Hi, I'm Sam. Nice to meet you all. I can see some familiar faces. Yes, so these days I'm a graphics architect at ARM. I work on trying to plot out where we should take the Mali GPU next, primarily. But my background is as a software graphics guy. I worked in the games industry for many years and then was head of technology at Enlighten, Geomerics, which we'll talk a bit later. And I only have a very brief moment to give you an overview of my job, and so this will be very brief, but I'm around all day, so feel free to call me and ask more detailed questions. We're going to give the briefest, quickest overview to Mali and tiling GPUs in particular, and then I'd like to give you a bit of an insight into power, which is something as a software developer I didn't give a damn about. That's the hardware guy's kind of problem, and unfortunately mobile flips this around quite considerably. So I'd like to show you a few bits and bobs from that, and a very brief mention of Vulkan, which is something that Khronos standards body are working on at the minute, and will come about next, or whenever it comes about. So I did try and look at all of the numbers of Mali GPUs that come out, and there's not a very simple way of explaining the numbering sequence, but basically there are three sort of tracks, if you want. There's and it's so small, thankfully, you can't even see it. But is there a laser pointer on here? Does that zap? Oh, there we go. There's some green things. These are the 400 series. Anything that begins with a 4. They are all primarily GLES 2. I think about them as GLES 2 devices, so that kind of class of hardware. And these are very, very low power, very, very common things, right now at least in the market. But then we have two other tracks. We have an area efficient track, and we have a power or best performance track, if you want. So all your high-end smartphones end up in this category, and then we kind of create area efficient versions of them in here, and this gives you your kind of high and mid, low end, right? In terms of numbers, if it's a number greater than 6, it's more likely to be a sort of a 6 plus something, or a 7, or soon to be 8. Then it's a GLES 3 device. Of which there are quite a lot now in the world. If it's a 4 series, then it's a GLES 2 kind of thing. But all of these devices are tile-based GPUs. So what is a tile-based GPU? I've been trying to perfect explaining tile-based GPUs because I end up doing it a lot in the smallest number of slides as possible. So here's my first attempt at it. This is what your simplified graphics pipe looks like. Your CPU generates some CPU commands, and a little bit of hardware assembles the triangles together and feeds the vertices through your first programmable stage of vertex shading. They then get rasterized, and then the pixel shader kicks in and shades the things, and then you need another bit of hardware down the bottom to merge the pixels together at the end and to blend them all. This sort of looks like you shouldn't need this stage in some sense, but all of this gets run in parallel and potentially out of order, and it just turns out to be much more efficient to have a kind of merging stage at the end. Now, I can kind of loopily group this into a command phase, followed by a geometry phase, things to do with geometry, followed by pixel processing phases. Now, the real pipelines are a lot more complicated than this, right? But they all follow this sort of bunch of geometry, bunch of pixel processing. Now, tile-based GPUs introduce slightly different things in that pipe. Now, they make the assumption that there are a lot more fragments or pixels in the world than there is geometry. Now, back when desktop GPUs were first designed, nobody knew that this would be the case. The triangle count's going to go insane. There'll be a bazillion triangles. We need to have all the triangle processing power in the world. Pixels are, that's just shading some stuff. And this is just not the case. There are moderate numbers of triangles, and there are bazillions of pixels. And pixel processing is all the rage, and so this turns out to be eminently true. And when this is true, tile-based GPUs win. But they introduce some slight extra restrictions. They work in a kind of phased fashion. So the clues in the title, they draw the screen in little tiny chunks. So to look at the pipeline again, what they do is they introduce some buffering. So before your command stream gets fed to the GPU, you buffer the whole thing up. And in particular, you buffer into what I'll call a render pass. A render pass is all the instructions required to draw an image. Not necessarily to draw all the images that it depends upon, but everything required to complete that one image. You just wait until the whole thing's there before you do anything whatsoever. Then you take all of the geometry and you transform and bin, either literally or logically, into screen space tiles. So one way or another, now you could have just done this and remembered the results and then thrown it all away, or you could have done it and actually stored the transform results somewhere, and there's lots of different variants on how different GPUs do this. In some sense, you should sort of treat it as magic, but what it does, it logically puts them all into bins. So every bin, every tile on the screen, has a complete list of everything that it needs to do to generate that image. Right? You're not allowed to look at other pixels that are being generated in flight, but you weren't allowed to do that in the original graphics pipeline anyway. And each of these tiles can now be processed completely in parallel. Now, this is not the case on an immediate style GPU, a desktop GPU, because what can happen is that you can be busy doing all your vertex processing as it comes in, streamed in from the CPU, probably with some buffering. But then what can happen is you could draw a triangle over the whole screen right at the end and just wreck everything. This can't happen under this scenario because we waited until we saw all the information. And if it is a triangle that covers the whole screen, well, then we just chuck everything else away that happened before it. Now, this allows us to be very, very bandwidth efficient because, I suppose I've missed this last bit, this stage here, right, the per tile shading part is just done on one core into fast local memory, and then the whole thing's flushed back when it's complete. There's no blending in and out of memory. There's no large amounts of bandwidth associated with it. Everything's kept nice and compact and local within each shader core, and then you just get the kind of final write back. And this turns out to be a colossal win. As an example of the Mali architecture, to take the latest one, the T880, there's a large bunch of shader cores. They're scalable. You'll find all sorts of different numbers in different GPUs all over the place. More cores is usually better. And in each core, you have a execution engine. Mali has this sort of tri-pipe idea. You have a bunch of different stages. You have arithmetic pipes that do maths. You have a load store unit for loading things in and out. And then you have a texture pipe for doing texturing operations. And this thing will try and keep instructions going down all of the pipes all the time to try and sort of maximize the whole thing. And you end up with all of your pixels, if you're doing fragment processing, being in a big pool at the top here. So let's say you have a 16 by 16 tile. You might have 256 threads, and they all just get fed through here as much as possible. And if they're doing a whole bunch of maths, well, thankfully we've got a few of these, and they all go down this pipes. But if they can do loads and stores and texturing operations at the same time, well, then they get fed down these pipes simultaneously. So the goal here is to just keep the whole thing busy as much as possible. Right? That's the job of GPUs. They're throughput processors. They don't care so much about latency. We just want to kind of keep the silicon busy and make it do work. But we also have this extra dedicated little bit over here called we call the tile buffer. Occasionally gets given different names, and extensions give it kind of different names. But it's a local bit of memory inside each core that has a copy of all the frame buffers you're currently working on. And these will be little tiny images, like 16 by 16 pixels, and if you're rendering to multiple render targets, it'll have multiple copies of them. And it'll have a local depth buffer and stencil buffer, and this is really fast to both read and write from. Now, there is also on the chip a dedicated hardware tiling unit. This is the thing that actually does the geometry binning. It's not something you can control really anyway, so it makes sense to just lock it down in hardware and flush everything through. You should sort of think about it as semi-being magic. There's also this funny kind of thing called forward pixel kill. Now, this is sort of like hierarchical Z, but on drugs. When you are drawing things, you don't necessarily know exactly what order all your triangles come in at, and you don't want to shade pixels that then get overwritten by other things. Well, given we have we have all the information on chip anyway, as we load in the geometry, we start rasterizing it, and the pipeline's quite long. It takes quite a while for those pixels to process, and they all kind of run in parallel. Now, if while we're doing that, we load another triangle, we say, this one's actually going to cover all these threads that we've already started. We just kill all the threads that we already started. So in practice, this gives you, it kills pixels that you've already started rendering, wherever they are in the pipeline, once you realize that something is going to overwrite them. So this, in practice, gives you a lot of overdraw reduction. It removes the need to try and figure out what Z is up front. So modern Mali architectures, not the 400 series, because that really was focused on extraordinarily low power, but all of the GLES 3 capable devices have this sort of overdraw reduction built into them. Another benefit of having the tile buffer on chip is that this is a reasonable bit of memory, and you can squeak in 4x MSAA. And because it's all there, and it's local, and it's dedicated hardware, doing MSAA is free. Obviously, anyone tells you that something's free, it's clearly not free, but it is the cost of doing MSAA is absorbed in the rest of the pipeline, right? It's like having lots of things running in parallel. Well, we can just do the MSAA part of this in parallel. We have the memory there on the side, and the hardware is there to do it, and so it really doesn't cost you very much at all. This is great for things like VR, which I'll talk a bit about later on. So no problem on Mali, just turn 4x MSAA on and everything should be fine. Now, this is obviously not the case on desktop GPUs because when you have 4x MSAA, you have to physically allocate 4 times the memory. And this is the problem with MSAA. It's a memory constrained thing. Turning on 16x MSAA is basically impossible on a desktop GPU or for any number of large resolution frame buffers because you just allocate all the memory in existence. On mobile, this is far less of a problem because that 4x only exists while it's in the tile buffer. The second this thing is done, well, it's done. I can just resolve, do the MSAA resolve, reduce it down to 1x, and that's what gets piped off chip. So it's both performant and bandwidth efficient. And there's a bunch of extra kind of cool stuff that you don't necessarily need to worry about, but being a mobile GPU, we care quite a lot about bandwidth, which I'll explain why in a second. And so there's some other kind of sneaky things. There's frame buffer compression, or AFBC, as it gets abbreviated to, which basically means anytime we write the fragments out from the chip, they get compressed before they even get losslessly compressed. Did I say that right? Lossless? Yes. Losslessly compressed across the memory bus. They're not then editable, but for render targets and things, this is all fine. This just happens magically. There's a thing called transaction elimination, which is really useful for UIs. And it works surprisingly well in games as well, which is a bit scary. Which is basically, if you're drawing something and you get to the end of drawing it and it's exactly the same thing that you drew the last frame, the same thing you already have in memory, well, we track some CRCs that tell us when it has or hasn't changed, and if it hasn't changed, then we don't stream it back across. This, again, is kind of transparent, but if you're drawing a UI and it doesn't change, you just don't pay the memory bandwidth for saving the thing back. This is great for the vast majority of mobile use cases where the image really is just the same. Games, it kicks in a surprising amount, which is a bit scary, as I said. And there's also ASTC, which there's a talk immediately after this on scalable text compression. So, power. Now, mobile is inherently constrained by the battery, at least if you want to run things forever, because obviously there's a finite amount of energy and doing work is going to consume it. But the thing that limits performance is not battery at all, it's power. In particular, heat power, not necessarily electrical power. It's a slight different. It's still joules per second, but we tend to measure a rule of. It's not an exact measurement. I don't know what the way you describe something where you measure something, but it's not exact. But anyway, there's a way of roughly categorizing heat power points in this thing called thermal design power, thermal design point, called TDP, and it tries to measure what is the capacity to dissipate heat of this device. And a desktop GPU, right, might have multiple fans and lots of very heavy metals in it and water whooshing past it and so on and so forth. And its capacity to generate heat is phenomenal. It can burn all the trees it likes. It's brilliant. Phones can't have a fan. Phones with fans doesn't sell, really. And they also can't get hot in your hand. If it becomes as hot as the palm of your hand, it starts to feel uncomfortable. People don't like to play with phones when they start burning them. And so phones are extraordinarily constrained by the ability to dissipate heat. The electricity is there and available, but you just can't use it on a sustained basis or your phone will get too hot. And this is 1 to 3 watts. To put it in tablets, they're bigger. So they don't have a fan, but you can dissipate more. It goes up to maybe 5 watts. Small tablets are 3, possibly. You could probably get larger than this, to be honest. Laptops, you start adding zeros, right? The leap, the second you can add a fan and it becomes large, is massive, right? An integrated desktop could go up to maybe 100 watts. A discrete GPU could be like 500 watts or some completely insane number. And so obviously, there's a large change here that to accommodate. And it just turns out that moving electricity around is the thing that generates heat, and so memory bandwidth, it becomes the most expensive thing in your system. I use a rule of thumb, which turns out to not be all that bad. If you speak to electrical engineers, they go, no, it's terrible. Don't stop telling people this, but it's actually quite useful, and if you just average all the numbers they give you, it gives you this number, which is that to move 1 gigabyte a second around the place will cost you about 100 milliwatts. And in a phone, well, how much could you spend on memory? Well, no more than the watt. So you're not going to get more than 10 gigabytes a second. Now, that is not where current consoles are, but that's not how you measure flops, right? So phones may well have advanced beyond the point of where Xbox 360 and PS3 were, but in terms of memory bandwidth, the power cost of doing this, the cost to dissipate the heat, is very different. And this gives a different environment in which you need to optimize. However, this is only true of the very high end. Low-end GPUs are actually constrained by die area. People want to manufacture them cheaply, and so you put down teeny tiny GPUs, but they actually swim in a big sea of bandwidth. So it's not common across all devices. High-end's constrained by heat, low-end's constrained by die area, which translates to just capacity. So I thought it might be educational to just have a look at the size of these things, right? Just for comical value, an NVIDIA Titan on the side, this is like a colossal thing, right? And then these are the sort of rough range of mobile GPUs. Now, this you should take with a big pinch of salt because sizes change by process, although surprisingly not as much as you might imagine because the second processes shrink, and so you can manufacture smaller transistors, people cram more in them. And so small things tend to come out about 3 millimeters squared. This is really small, entry-level phones. And then the most common range is sort of 5 to 10 mils. This is the vast majority of Android phones in the world. This would be a pretty decently performing thing. This not so much because you've lopped half of it off, but it's still still a fairly capable device. And then the high end, this is really this kind of mysterious figure. 30 millimeters squared is probably somewhere in the average, but people sometimes build absolutely colossal mobile phone GPUs. And this number could go up and down depending on how important people feel GPUs are in mobile phones. I see some frightening projections of what people really might intend on putting down. But they could also be smaller than this. And on smaller, more modern processors, you can get a lot into a smaller area. But the thing I'd like to illustrate is that there's an order of magnitude between the top and the bottom here, just in a phone. Now, these are things that run the same APIs. They can all be Glaz 3 capable. They all have exactly the same feature set. But clearly, you can't chop 9/10 of a GPU off and have it work at exactly the same rate. So GPU feature set can't indicate performance. Actually, measuring performance turns out to be quite tricky, and it's just a problem because there are just so many phones in the world, and it's such a large market to sell into. What a terrible problem to have. Thermal throttling. So if you don't see charts like this very often, I find them interesting as a software developer, so I thought I would show you one. What actually happens if you run a whole load of content on a real system for a while? All hardware has this ability to do what they call DVFS, dynamic voltage frequency scaling. Basically says, well, I can't allow the device to get hotter than this temperature. I have a thermal limit. And the second I start approaching that, I have to slow things down, potentially to a crawl or stop things working in order to remain under that temperature. And so if I was to run a benchmark, and this is on an old device with an old benchmark, for the first period, I can run everything completely flat out. It looks great. Right? The blue line here is the big cores Chris was talking about earlier. The green ones, the small cores, and the GPU, and given this is a graphics benchmark, right, is presumably the thing that we care to keep maximized, are all running lovely, except this is unsustainable, and it's getting hotter and hotter and hotter, and at some point something has to give. And so in the next period, the first thing that gets clawed back are the power optimized big cores. They come down first. Little cores, not so much, will they start to waver a little bit. But obviously, we were maximizing everything to begin with, but now we have to kind of cut back, got to be a bit more frugal. Big things go first. Although the GPU, well, that still remains pretty high up. That's all great. This is fine, right? It's everything working as it should do. This bit is much less fun. Now, here, what's happening is, for whatever reason, I don't quite know exactly what happened in the benchmark at this point, but some content decided that it's going to go completely crazy on the CPUs, and they hog all of the big cores, and the system realizes that it needs to spin up the big cores and put all of the power into that to get the job done as quickly as possible, at the expense of slowing down the GPU. And this is probably, now, this might well be the thing that you want to happen in some other circumstance, right? But if you have the knowledge that you're a graphics benchmark, and that graphics is what you care about, then perhaps this is something that you would at least like to know about. Because what you could very well do is start saying, oh dear, I'm doing too much GPU work, I shall start cutting back on that. Whereas the actual problem is that you're doing too much CPU work and it's hogging all the thermal headroom. Now, you might say at this point, so, Chris lied to us. He told us we should trust the scheduler. Give us back all the controls. I think the argument is slightly more delicate than this. This is what you're asking the system to do. It's just not necessarily transparent from the outside that what you're asking to do is a sensible thing. And so there is some care on the part of the user here to realize when you are which parts of the SOC are consuming your thermal headroom to avoid this kind of scenario. It's a tricky problem, but it's a complicated world. And in the long run, well, we have to remain within thermal limits. Things get slowed down a bit. I arguably like to see this a bit more pegged, but if we run out of thermal headroom, then the only way to really cut this back is to do less work. Now, if you care to run over long, sustained periods of time, then you have to look not at the performance of your workload when you first run it up, because otherwise you're measuring this when everything's brilliant and everything's amazing, but you need to measure it after a minute or so when it's hit a kind of steady state. That's the point at which you actually know how well balanced your system is. And as you can see, it's not necessarily 100% stable because it's optimizing for power and energy efficiency, not necessarily optimizing for fully stable operation because your workload is changing. And that creates some interesting problems, shall we say. And I'll come back to that in a later talk today in terms of VR. But for today, I'll close by just mentioning the efforts that are going on currently to bring up Vulkan. So GLES APIs that exist currently are lovely in the sense that they're simplish to use and they're familiar, but they make the CPUs do a lot of work, and they are not multi-threaded, and they have hidden costs. And they're also designed in an environment where tile-based GPUs were uncommon to some degree, and so they don't have, what I was talking about earlier, is this explicit notion of a render pass, right? On the CPU, we had to buffer all the commands into a render pass's worth of work before doing something. There's nothing in GLES API, the OpenGLES APIs that talk about render passes at all. You have to sort of know that certain operations will cause the end of a render pass to occur. So you have to be quite careful about what state you set and exactly when you set it. Whereas in Vulkan, it all becomes completely explicit. And there's some extra cool benefits to having it being explicit. When you give the compiler more information, it can actually fuse some render passes together under some circumstances, which we don't have time to go into today, sadly, but we'll talk much more about next year. Obviously, it has certain hidden costs. Because it tries to make things simple for you, you could change some states, or you could try and update a texture, but it's already being used by the GPU, so the driver is forced to make a copy. These things incur hidden costs, and you'll see it just in the fact that a draw call does not cost the same amount all the times you measure it. Now, this can be a bit annoying when you're trying to iron out why does the game stutter when this and this and this and this happens, and there's very little visibility of it because all of it's held within the driver. There will be good reasons why it happens, but it's not evident in the API. So all the notion of making these things explicit in the API should actually make it a lot simpler to develop for, although I should say that Vulkan is very much a gloves-off API. There is very little protection between your shotgun on your feet, and so there will be more information on how to avoid removing limbs post-release. But the main benefits of it will come from the low overhead, the amount of CPU stuff we just don't have to do, the ability to spread things across multiple threads, which I think would be a huge win. Draw calls are a problem, not because people are bad at writing drivers, but primarily because the API requires the driver to do a lot of work. And we finally get to a point where tile-based rendering actually becomes a first-class citizen in the API, and we can start to really capitalize on that. So I will call it there for a day. I am around. I don't know if we have time for questions.
Does any hands want to shoot up? Ooh, fantastic. Marmalade at the back.
No, it was a quick question about Vulkan, really. I mean, looking at your roadmap, obviously 400 was OpenGLES 2 and the next version was OpenGLES 3. can we assume that Vulkan's going to require another hardware architecture, or is it anyway backwards compatible to an existing GPU?
I forget exactly what official statement has been made on it, but the intention is to build it on existing hardware. So it's not a breaking change in the API, but it's not a change in everything at the same time. I don't know. I don't know what they've said. They may well have made a public statement if anyone else knows and can call out. But they have not made It's not new hardware coming out now. It's hardware that has already shipped that will be able to support it.
Did I see another hand shoot up, or was that was it? Okay, well, thank you so much, Sam.
Thank you.
Put that there.